I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to discuss the topic General Solution of a Transmission Line for the course Transmission Lines and Antennas. So, in this picture, there are two diagrams. Left hand side, we have an ordinary electronic circuit which consists of the lumped components, and this type of circuit is the form of a network of lumped elements or lumped circuit. On the right hand side we have a transmission line model, and in the transmission line all the parameters like resistors, inductance and capacitance are uniformly distributed throughout the length of the transmission line. So they are called as the distributed networks. So there are two types of networks. One is lumped network and distributed network. The difference is a network which is formed by lumped components like resistors, capacitors and inductors are the example for lumped network, and a network which is formed by using sections of transmission line is called distributed network. And in the lumped network, the parameters can be easily determined because they are fixed at discrete points in the circuit. But in distributed network, parameters are distributed throughout the length of the transmission line. So, and in lumped network, one can easily recognize the presence of the components like resistor, capacitor and inductor. Example are ordinary electric circuit. But in distributed network, it is difficult to recognize the presence of components like resistor, inductors and capacitors. Example, transmission lines. So transmission lines general solution is very important to understand the behavior of a transmission line, and it is also used to find the voltage and current at any point on a transmission line. So we know the line parameters we discussed in the previous video. R is the series resistance, L series inductance, C capacitance between conductors, and G is the shunt linkage conductance, Z is series impedance, omega L is series resistance, and Y is the shunt admittance, S is the distance to the point of observation measured from the receiving end of the transmission line, omega C is the shunt susceptance, I is the current in the line at any point, E is voltage between the conductors at any point, L is the length of the line. So in order to find the transmission line general solution, throughout the entire line a small segment is taken with series resistance and series inductance, shunt conductance and shunt capacitance. And this is the equivalent diagram. We have the series impedance ZDS ohms, shunt admittance of this elemental section is YDS ohms, the input voltage is ES, voltage at the transmission line is E, input current is IS, current through the transmission line is I, the receiving end current is IR, and ZR is the impedance, that is the load impedance. S is the distance from the receiving end to the point of observation, and the section elemental section which we have taken for the observation length is taken as ds. So now as the first part of transmission line general solution, we should identify the voltage drop in the line. So here this incremental section is of length ds and carries current I. The series line impedance is Z ohms and the voltage drop in the length is ds. So here dE is given by the voltage IZ into ds. So we get dE by ds is IZ, and current across the line is dI, it is EY into ds. Here E is the voltage, YDS is shunt admittance. So dI by ds is EY. So now the equation 2 and equation 4 are differentiated with respect to the distance parameter S. So we are getting d squared E by ds squared is Z into dI by ds. We know dI by ds is EY and it is substituted, and similarly d squared I by ds squared is y into iz. And now these two it is this differential equation is is solved, that is d squared e by dz squared is taken as m squared minus zy into e is equal to 0. So by solving this second order differential equation, we get the answer as m is equal to plus or minus root of zy. So if we are getting the answer for second order differential equation plus or minus root zy, we have to write the form as the exponential form. One is having plus sign and another term is having minus sign. So the final solution for voltage is E is equal to AE root zy into S plus BE minus root zy into S. Similarly, we can write the current equation with parameters C and D. So this parameters A, B, C, D are called as arbitrary constants of integration. So now in order to further solve the equation, we are assigning some conditions. So since the distance measured from the receiving end of the line, at the receiving end the distance is 0 because it is the starting point. So S is taken as 0, and at the receiving point we know I is equal to IR, E is equal to ER. By substituting these equations, these conditions in equations 9 and 10, we get the receiving voltage ER is A plus B, because in the exponential form we substitute e power 0 is equal to 1, and the receiving current is C plus D. Taking this equation as equation 11 and equation 12, and these equations are again solved with respect to differentiating with respect to S. So we get dE by ds and di by ds. We know dE by ds is Iz. So and from the Iz equation we can easily get I. Similarly, from we can get E as C into root of zy e power root zys minus D into root of e power minus root zy into S. So here also we are getting the conditions at the final end, that is at the receiving end. We get ER is C into root of zy minus D into root of z by y, and IR is A into root of y by z minus B into root of y by z. So by solving these equations, we get the ABCD values, the arbitrary constant values. A as ER by 2 plus IR by 2 root of z by y, or by substituting IR as ER by ZR and root of z by y is Z0, we get the values are ER by 2 into 1 plus Z0 by ZR. In this way, B, C, D values are formed, and finally by substituting all these values in the voltage and current equation, we get two forms of equations, two sets of equations. One form consists of exponential term and another form is consist of hyperbolic term. So the first general solution of voltage and current at any point on a transmission line, E is equal to ER by 2 ZR into ZR plus Z0 e power root of ZYS plus ZR minus Z0 ZR plus Z0 e power minus root ZY into S. And similarly, the current is IR into ZR plus Z0 by 2 Z0 multiplied by e power root ZY into S minus ZR minus Z0 by ZR plus Z0 e power minus root ZY into S. And in the another form, we get the terms in terms of cos h and sin h. So the voltage equation E is ER into cos h root of ZY into S plus IR into Z0 sin h root ZY into S. And current is I is equal to IR into cos h root of ZYS plus ER by Z0 sin h root of ZY into S. And these two forms of voltage and current equations are called as transmission line general solutions. So the final solution, applications of transmission lines, they are used to transmit the signal, that is in the form of electromagnetic waves, from one point to another point. They can be used for impedance matching purpose. They can be used as stubs by properly adjusting their lengths. Assessment questions. In these questions, we know the lumped and distributed networks, need of a general solution for identifying the behavior, and the parameters of the transmission line we know RLGC, and the assumptions at the receiving end we know that S equal to 0, I is equal to IR, E is equal to ER, and we have the two forms of transmission line general equations for the fifth assessment questions. Thank you.